Welcome to the next part of Stl.Fusion tutorial, and today I'm going to talk about the state. So that's probably the last missing piece that you need to start building UIs and full-blown apps on Stl.Fusion. And or at least if you use server-side Blazor, that's definitely the last piece. If you want to use client-side Blazor, then or Blazor WebAssembly, then you need to wait for like the next part. Okay, so state is an abstraction that allows to track the most recent version of a computed instance that is tied to certain computation. In reality, it doesn't track the most recent version of any computer, but it tracks the most recent version of kind of its own computer, the computer that's associated with this state. But nevertheless, it doesn't change much because like this computer can build its own state the same way as any other computed value, like by composing it or by simply copying some other computed, and so it's basically doesn't change anything. Okay, and as usual, there is an interface called iState of T, and a few versions of state or flavors of the state, mutable state, like actually you need just mutable state and live state. Even though if you look at subdivision further, then live state is computed state, which means that this state is derived from something. And mutable state is state you can simply set to change its value. Okay, so and yeah, as with almost anything else in Fusion, or like with many other things, like iResult or iComputed, there is a typed and untyped version of this interface, and some other things you need to know about. But first, let's start from an example. And I'll start from exactly the one presented in this part of the tutorial first. But this time I already created the console app project for this part of the tutorial. So I'm going to simply run it, I guess. And yeah, that's the example. Maybe I forgot to mention, to create state, you typically use this construction, though in reality, get state factory is a shortcut that simply pulls the iState factory instance from your service provider. And the reason you need it is, like, technically you can create a state with new, like you can type here and you will just have to provide a little bit more options in this case, and basically it's not as convenient as using state factory. And any state, it knows a service provider because it basically has to know it to discover other Fusion services and to pull other Fusion services from it. So ultimately, it's easier to use state factory to create state instances. But nothing prevents you both doing this manually or, let's say, even subclassing one of these types, like, let's say, mutable state or whatever you prefer, and creating your own kinds of state. So let's look at this example. Basically, it creates a mutable state. It gets the computer associated with this state, then like writes the state, sets its value to another one, writes it again, and also prints the volt computed. And if you look at the output, and you will see that, okay, like it started from printing 1, which was actually set here, right? I mean, it was the initial value, and later it was replaced with 2, right? The old computer is obviously still available, but it's in invalidated state. So basically, it like mutable state is variable, right? And maybe to fully demonstrate this, let's actually do something that is not presented in this part of the tutorial. Let's add private variable here, right? And we will initialize it for the constructor. So we need iState factory to initialize it, but and I guess and all we need here is initial offset. Let's say we set it to 0, right? So interesting that since all this stuff is backed by computed values, then you can use it in, let's say, this method. And so interesting that I actually can't write just offset value here. Or actually, let me show what's going to happen if I do this. So let's pull and yeah, now this will work, but only if I do this, I guess, right? And this one could be asynchronous. Okay, so let's. Oh, I actually need to expose it somehow, right? Let's make it public. And now we can change its value here, right? So, and let's see if something is going to change once we call it the second time. It's weird, right? It prints 0, even though we were using it here. So the interesting part is, so since value, even though value is kind of value is taken from some computer, the logic that sets up a dependency chain doesn't work if you just access a value of some computed here. What you need to write, if you really have a computed here, like set computed. And you need to put a weight. So this is where you need to, interesting, can I do this? Yeah. So for state, you can, there is a shortcut that actually routes the same call to computed. But overall, so what you need to do is to use state in this way if you want it to become a dependency of result of this call. And now as you see, the second call produced a different value, right? And moreover, you can even capture a computed value behind this thing, right? As you go over. And so basically, yeah, it's a installation, and I'm not going to show it. It puts await here, and then I can print and let's just print computed twice here to show what's going on, right? And so as you see, first it was consistent, then it became invalidated. So clearly the output becomes a dependent, the output of this call becomes dependent on state, right? And once I change the state, I mean this part, then like basically this output changed. Okay, so let's move on and let's see what else is there. And yeah, I never. This is another good example. It's actually about exception handling, and I'll show it a little bit differently because it works kind of well. First, it makes sense to show how it works with regular I computers, right? Let's see. What can we do here? Okay, so now we can check out what's going to happen if we do this thing, right? Yeah, okay. First, we got an exception. And, wow, did you see this? The cat just disappeared and or maybe it turned into a blanket. So that's clearly a glitch in the matrix. And the reason glitch happened is well, yesterday I found a bug in my code, and moreover this example is actually a little bit more interesting and tricky than it seems. So right now I'm going to explain what actually what happened and like what's going on. But first, let me run the new example, and right now it prints kind of seemingly correct 2 lines, right? At least there is no exception. Earlier, the exception was happening in this method because this one was throwing an error, and it's wrong because if you intend to capture a computed value behind some computation, uh, these things still should work despite the fact that the computation itself throws an error, so it shouldn't throw an exception. You still should get a computed which has an error property set. But so it's the same as, let's say, you call like a task to a toll or something. You are not expected to get an exception, right? In case like this. So anyway, that's the first thing. The second interesting thing is, so what I intend to do here is to change the value of set, right? And if you look here, we use offset in this method. So the assumption is like after I change this value, this same thing becomes invalidated, but it's not. Like, so what's going on? And let's actually do one interesting thing first. So first let's call counters.increment a. Oh wait, here, and comment out this thing. So as you see right now, it's invalidated. So why it doesn't work with offset the same way? And the answer is, if you look at this code, you will see that we use offset after the fact, after the moment we throw an error, which means that like once, in case this condition is true, offset is not used. So now it's interesting, like, okay, so we get a case when, and like, or maybe, what if we do even this? Like, what if we put this right on the first line and run the stuff, right? Basically, now it doesn't matter what we do here, we get basically, oh, so this thing works because increment explicitly invalidates this method, and basically that doesn't matter, right? But on the other hand, like this part, I mean, where we get a dependency is basically untouched yet. So like, is it even, I guess, normal that we still see a consistent value? And maybe more interesting question is, well, what if we, in general, like get an error? So let's say we do nothing, and like, are we supposed to basically, as you see when we call this thing, or like, we don't call it here, but let's say, let's actually call it for the second time, right? And let's get to the second thing to do, right? Because and as you see, the second call, it doesn't even happen. So the question is like, if we throw an error, for how long we think is supposed to stay basically the same? And because for a regular result, it will stay the same indefinitely unless some dependencies change. But what about errors? Is it like kind of a good idea to basically assume that an error as a result of calculation should also be cached indefinitely, or like basically for fairly long time maybe? And is it normal? So interestingly, the answer is no, it wouldn't be cached indefinitely. And there is a special logic that, and even special options that control this. And now I'll show you how it works. So let's leave this into the, let's put it away. So let's put this thing here. So if it would be a normal result, it would never, so let me show you. So this is a normal result, and basically it never stops. Unless we change something, this thing wouldn't change, so nothing invalidates this thing, right? But if it's an error, it gets invalidated approximately in 1 second, and the reason is, so that's 3 seconds right now. So there is an option that controls this, and so right now the delay should be 3 seconds, right? 2, 3, yeah. Or like you can put it 0.1, and you will see it's almost instant. Okay, you can put it, you can put 0 here, and in this case it will immediately invalidate. So the point is, you can control for how long the error result stays kind of the same. And you can also put, like if you put, I think, max. Oh, okay. So this is that. I think something like this. You put max value. Okay, no. Yeah, that's weird. But basically, yeah, maybe I should actually handle this. So basically, it should be indefinitely. But anyway, maybe I'll change this later. The point is, if you put some high value here, then this thing is going to auto-invalidate after a fairly long period of time, I guess. Okay, so what else is interesting here? Let's remove this thing first, and let's actually. So can we make this introduce variable? So if we put this thing before the part that throws an error, right? Then there will be no delay, and basically this thing should be invalidated at this point, I guess, already, right? Okay. So my point was, if you don't capture some dependency, then I guess this result is not going to be invalidated because it changes. And in this case, the dependency is a mutable state, right? Okay. As for errors, then you can basically, there is a special option that tells when to invalidate a result, which is an error. Okay, now let's look at the, actually let's run, now let's copy the second example. So we were mostly talking about the first one, but I went a little bit sideways and decided to explain this concept, like how computed of T handles errors. Now let's see how state handles errors, and let's run this example. So what do we actually do here? So this thing isn't used. We basically create a state, and its value is 0 by default. It's a mutable state. Then we set it to error, and then we here we access its value property, and as per iResult contract, value property should throw an error, and we catch this error here and print this message first and this message. So this is exactly what happens here. Basically, this line responds to this output, right? And this line responds to this output. And that's how it works. But one interesting part about this example is that any state has last value property and last value computed. So last value stores last valid value. Valid means non-error. And last value computed is a computed that's kind of that actually stores this value. And let me show you. So right now it prints 0, right? But if you set, let's say, state 5 year and run the same code, then last value will be 5, and last value computed will be basically the computed matching this 5. So this thing is actually quite useful in UI, because typically what you use in the UI and or like if you bind some UI controls to some values, then usually you need this one or like this one. And last but not least, there is also, so any state has a snapshot property. So let me show you here why it makes sense to use snapshot. So let's say we have this code. Let's say, so if we run it like right now, everything is fine, right? And it just doesn't print value because here state doesn't have value; it has an error. But the point is, so state may change between this evaluation and this evaluation. And let's say if it had value at some point here, then it could have an error here and this thing would fail. So the correct way to handle scenarios like this, I mean, to get a stable view of a state is to write something like this. And then write this is a correct way of doing this. You can also use snapshot computed, like C, and then you could use C. This is also correct, but my point is if you would, so computed, it can't, it's immutable thing, right? And it can't change its value during runtime. Same for the snapshot, but it's not applicable to the state itself, which is not. So state is mutable, and you should take this into account. Okay, let's get to the last example here, and this one. And so far we were talking about mutable state, right? But there is another kind of state called live state. That's the way you create it. Let me show. So first, let me kind of explain what's going on here. We basically let's just state for simplicity. So we create live state here, and this piece configures its options. So since we don't want to tweak options of the state during runtime, like in runtime when it's already created, there are some objects that use this pattern when you pass an options object in construction, in constructor, and or like when you construct it, and basically that's the way to configure the instance of state, and you can't tweak it much later. This is the function that actually computes the value of the state using some other, maybe using some other computed values or like compute services. So what can we state? So let's run it first. So basically, first we create this thing, and maybe one last thing. So this part would be written here as well, and it's nearly as good as like writing it in options. The difference is if you write it here, then probably some of these events will be missed because the state, once you create it, it kind of instantly enters this update loop, and basically you might expect that, let's say, invalidated and updated, some events will happen, let's say, here. Okay. But so if you want these event handlers to be about before, so that they catch every event, then you should pass them in options. But like you can do this later as well. In this case, I guess it's fine. Anyway, So when live state is created, I guess this is a synchronous method, right? There is no await or something, which means that we can't compute the real state at this point, right? Because like it should complete quickly, and computations like this thing, it's asynchronous. So this means that if you will observe the, and let's actually look at what's going on here. So basically, when live state is created, first updated event is raised, right? And basically it says that the value is either empty string or null. In reality, it's null, right? And the initial state is consistent, but it immediately turns inconsistent. And that's basically the, let me actually run it once more. So yeah, so you see now basically these two first two lines, they disappeared because all these events, like first basically the first update, it happened while this thing runs. And since handlers were attached later, they missed these two events. But ultimately, what I was showing is that the state is born inconsistent, and basically the computer has default value and it's inconsistent. As for the what happens next, so by default, the update is triggered immediately. I mean, the first update on the state, it kind of runs right after you basically create the state. And so this is one way to wait for its completion. But like if you will, let's say, put something like wait, then it will also complete here. So basically the output will be pretty much the same. So you see that like before, so you see that before the update, then this line is printed, then the update happens, right? And this line printed. So let's run the same code. So you see that this get async, right, and updated, it actually happened while we were waiting for 100 milliseconds, which means that the update was kind of triggered immediately for this state, and because it was inconsistent, and there is no update delay for the first update. Again, by default, so you can control this. You can put something like, let's say, delay first update true. And in this case, you wouldn't see this, right? Before, after. Because default update delay, or like in this case, update delay is 1 second, right? But by default, first delay is not updated. So sorry, the first update is not delayed. Anyway, let me show what's next. And all of this means that, like, normally if you need a fully kind of updated state, then the right way to do this is to actually write something like this. So first we correctly set, we switch back to correct setup of event handlers. Then we type update async here, false, and await here. So in this case, I'll get a fully updated state right before the increment. So yeah. So basically that was the update. And like right now you see that the state is born in consistent state, immediately invalidated, then the update was triggered, and so all of this happened before this increment, this line, which means that basically all these things were a part of kind of construction that we were using here. Okay, so what's next? So when we increment A, and as you see, the state was computed as basically like we just get a counter named A, right? And return a string that uses a value of this counter. So interestingly, when we incremented the counter, state was immediately invalidated after that and updated in 1 second, right? And that was, I guess, the intent, so that there is 1 second delay. If you put 2 seconds here, let's extend a little bit which as well. So 16, 18, 2 second delay. So that's what update delayer does. And typically, you don't want to update the state immediately. The only case where you want to update the state immediately, I mean, let me clarify, what actually is going on. So technically, the state doesn't know what triggered the update, right? It just, or like what triggered the invalidation. It just get invalidation notification, like its computer gets invalidated because, like in reality, this computer was invalidated, and it's basically cascading invalidation. And then, like, the next question is, so how long should I wait till I update it? Because, like, the delay is actually the only thing you can control. You can either start it immediately or maybe wait but for how long? And this abstraction, I mean, so this thing with update delayer, it actually configures which update delayer to use and how to configure this update delayer, so you can see all the overloads of this thing, but overall you can pass even your own update delayer and decide for how long to wait. And I also recommend you to even look at what update delayer is. Basically, this is the type, and by the way, that's the interface update delayer has. Delay, sync, and cancel delays. Let me show how cancel delays works. So typically, you want a delay because typically the update is triggered by something else. It's like maybe actions of some other user or something else, and ultimately you want to show this update, but probably not instantly, right? On the other hand, what if like the current user just performed an action and you want this update to be instant? This is what you do. Like, you know that this action is like basically like you can see, like, you can check out the code of samples and you will see that exactly something like this is happening there. So first we take an action, or like we run an action, and then we call this state delay, cancel delays. So you saw that just before this run, the delay was 2 seconds, right? I mean, invalidated, updated. Let's run it. So instant, no delay, and this is how it works. This thing basically starts the delay ticking on the state, but this line just cancels the active delay. And typically, this is what you want to use in the UI when your current user takes an action. You just cancel all the delays. And for the sake of clarity, you can have a single update delayer used by your whole UI, or like by maybe the current part of the UI everywhere, by every control, and so on. So you control all of this. Okay. And I guess that's mostly, let me check out what else is there. Well, I think I just covered everything related to state, usable state, live state. Oh, there's also live state with T-locals, and in fact, it's a live state plus a mutable state. I don't know if it's worth showing it. Let's actually, well, let me show you very quickly. So Spring. And so I created a little bit different state right now. And here, the second parameter is, let me actually state. So if you use the second parameter here, then your state will get basically this thing, and you can freely use it here. You don't have to write something like use async for locals, because by default it's a dependency. Even though if you want, you can kind of cancel this thing by typing options. Let's say, and you set all of these things to false, but like usually it doesn't make sense. So the reason this thing is useful is like usually if it's a state of some UI component, then locals is the client-side state of UI component, which once you change, you want this thing to be invalidated and recomputed. Let me show you how this thing works. Oh, and by the way, when you update locals, so let's stay locals. And I don't think we need any delays, but actually let's just leave a small delay in the end. So you see, that's the first value that was actually computed, right? And this is the, oh my God. So that was a typo. So you need to use value, right? So the first value we computed was this one, and that's the second value that was recomputed because we updated locals. And for the sake of clarity, there is no delay if you update locals because the assumption is, again, it's a client-side action or something like this. Basically, when you update locals, usually it's user action or something, and it doesn't make sense to have a delay. That's it. Okay, thanks for watching this part.